Welcome to The Explainer. Today we're decoding the invisible mechanical explosions happening literally thousands of times a minute right under your car's hood. I mean, have you ever turned a key or pressed an ignition button and just wondered how liquid fuel is miraculously transformed into the sheer forward motion of a heavy metal machine? Well, you're in the exact right place. We're going to unpack the fascinating engineering magic that powers our world. Let's get right into it. Here is our game plan for today. First, engine basics, the strokes. Second, we'll look at the Otto versus Diesel cycles. Third is the efficiency battle. And finally, number 4, fuel injectors in diesel. Okay, diving right into section 1, engine basics, the strokes. You can really think of an engine as this brilliant, repeating air pump that turns small explosions into rotational movement. It's basically a 4-step mechanical dance. Step 1 is the intake stroke. The piston drops down, opens a valve, and physically sucks in air. Step 2 is compression. The piston comes back up, squeezing that air and fuel mixture super tight, which drives up its temperature and pressure. Then, boom, the magic happens in step 3, the power stroke. The mixture ignites, the high-pressure gas violently expands and forces that piston right back down. Finally, step 4 is exhaust, pushing the burnt, spent gases out so the engine can take a fresh breath and do the whole shebang all over again. But why do we have different engine designs? If we look at this comparison between a 2-stroke and the 4-stroke we just talked about, the engineering trade-offs are wild. A 2-stroke gives you a power cycle for every single revolution of the crankshaft. Because it uses simple ports instead of complex valves, it generates high torque and is cheap, light, and easy to build. But, and it's a big but, it mixes lubricating oil directly right into the fuel. That means some oil just burns away, causing way more smoke, more noise, and a lot more wear and tear. The 4-stroke, on the other hand, needs 2 full crankshaft revolutions per power stroke. It's definitely heavier and pricier to manufacture, but it delivers dramatically higher thermal efficiency and a much longer lifespan. It's a classic engineering trade-off.
All right, let's move on to section 2, Otto versus Diesel cycles.
To really understand these engines, we gotta go back in time a bit. In 1876, Nicholas Otto proposed the Otto Cycle, which laid the absolute groundwork for the modern gasoline engine. It was a massive breakthrough. But, Dr. Rudolf Diesel wasn't completely satisfied with the efficiency limits of Otto's design. He kept pushing, and his relentless pursuit of perfection led him to introduce his own revolutionary cycle over 20 years later in 1897. So we basically have 2 brilliant inventors with 2 radically different ways of turning chemical energy into motion. And the absolute core difference here, it's how they actually ignite their fuel. The Otto cycle requires a little help to get the fire started. It uses a spark plug to ignite a pre-mixed charge of air and fuel. But the diesel cycle, it's a compression ignition system. Get this, it doesn't need a spark plug at all. None. Instead, it relies purely on the extreme heat generated by squeezing the air inside the cylinder to self-ignite the fuel the exact microsecond it's injected. It just explodes purely from pressure, which is absolutely fascinating. And check out this number on the screen because it really tells the story. 22.1 to 1. That is a massive compression ratio for the diesel cycle. To put that into perspective, an Otto cycle engine is usually sitting way down around 11 to 1. This extreme squeezing in the diesel engine is exactly why the air gets so incredibly hot that it can self-ignite without any spark. This massive compression is the defining secret behind the diesel engine's immense torque, power, and heavy-duty capability.
Which perfectly sets up section 3, the efficiency battle.
So, how do these cycles dictate efficiency? Look at these PV diagrams. It all comes down to how heat is added to the system. In the Otto cycle, it happens at a constant volume. The fuel explodes so fast, it's like a sudden bang in a closed box. The piston hasn't even had time to move down yet, so you get this incredibly sharp, sudden pressure spike. Diesel, on the other hand, adds heat at a constant pressure. It's a bit more of a controlled, slow burn while the fuel is being actively injected, so the volume is actually increasing as the piston gets pushed down. This, combined with that crazy high compression ratio we just talked about, translates into the diesel cycle being up to 40% more efficient than the Otto cycle. 40%! That is huge! But the efficiency battle isn't just about thermodynamics. Petrol engines actually waste a ton of energy fighting what engineers call pumping losses. The folks at Autocar have this brilliant analogy. They compare it to trying to suck a drink through a squash straw. It's exhausting, right? Petrol engines running the Otto cycle have to constantly throttle or restrict the incoming air to maintain a very specific 14.7 to 1 air-to-fuel ratio. But diesel engines, they run super lean and are completely unthrottled. They just gulp down as much limitless air as they want, and they control their powers simply by varying the amount of fuel injected.
breathing without a squash straw drastically cuts down on wasted energy.
Let's wrap things up with Section 4, fuel injectors in diesel.
For Dr. Diesel's cycle to even work today, it relies on this high-speed mechanical ballet we call direct injection. The engine control unit, or ECU, acts as the absolute brain of the operation. The fuel pump sends highly pressurized fuel to the injectors. Then, analyzing real-time data from air temperature, engine speed, and exhaust sensors, the ECU decides the exact microsecond to act. The injector fires the fuel directly into the high-pressure combustion chamber, where it violently mixes with that superheated air and instantly combusts.
Now, keep in mind, diesel fuel is naturally denser and heavier than petrol. Because of that, these injectors have to operate under absolutely immense pressure to reduce that heavy fuel into a perfectly fine mist. If the injector just squirted a solid, sloppy stream of diesel in there, no way would it burn cleanly or trigger that signature compression ignition. It has to be perfectly atomized. That's why if a diesel fuel injector gets clogged or starts failing, you instantly get rough idling, misfires, terrible fuel economy, and awful emissions. Maintaining these high-pressure marvels is absolutely critical to the health of the engine.
So what does this all mean for you? Take a moment and ask yourself, how does this invisible thermodynamic dance dictate the performance, the fuel economy, and even the maintenance costs of your next vehicle? Whether you prefer the smooth, high-revving nature of an Otto Cycle petrol engine or the unthrottled, high-compression efficiency of a diesel, these invisible engineering battles literally define the cars we drive every single day. Thank you so much for joining me on this explainer. Keep asking questions, and I'll catch you next time as we continue unpacking the mechanical magic of our world.